Hello everyone, thank the organizers for giving me this opportunity, and it's a pleasure to be here to present our paper. My name is Liu Wei, a PhD student at CCGrid, LCTS, and BDTS. I come from Huazhong University of Science and Technology, Wuhan, China. As you know, Wuhan is a beautiful city with a long history which locates in the central part of China. Now, I'm going to talk about our recent work named Straggler-Aware parallel graph processing in hybrid memory system. As you know, graph processing has a great application future and a very attractive practice for big data analytics, such as social networks, scientific computing, and recommendation systems can all be described as graphs. To process large-scale graph data efficiently, it is essential to employ an in-memory computing paradigm. However, DRAM-based single-machine graph systems, such as Straggler and Java, face scalability problems due to high power consumption and limited memory density. Luckily, emergency NVM technologies such as PCM, ReRAM, and DCP-MM can provide a higher memory density than DRAM. The hybrid memory system composed of NVM and DRAM has become a promising solution for building in-memory graph systems. However, NVM faces higher access latency and lower memory bandwidth than DRAM, causing new challenges to graph processing. Our work is to address the problem posed by this new memory architecture. My talk has 4 parts. First of all, I will present the background of NVM technology and the challenge and motivations of using hybrid memory for graph processing. Second, I will show our design of NVM graph, which is a scheme to address memory load imbalance caused by the hybrid memory. Then, I will show the evaluations of NVM graph through extensive experiments. Finally, I will conclude our work. Let's move to the first part. Generally, NVM have higher memory density than DRAM, but at the expense of higher access latency and lower memory bandwidth. Inter-op DCP-MM is representative of commercial NVM. As the table shows, the random read latency of inter-DCP-MM is about 4 times higher than that of DRAM. The random read-write bandwidth of DCP-MM is much lower than that of sequential read-write, especially 5 times for write. The first challenge of graph processing or hybrid memory is the memory load imbalance. When graph data is processed in a hybrid memory system, the whole graph should be split into different partitions and assigned to DRAM and NVM. Besides the CPU load imbalance, the difference of time spent in processing the same data in DRAM and NVM will cause memory load imbalance. The first figure shows the load imbalance problem. The number in the box represents the size of data to be processed in a partition. The number beside the arrow represents the processing speed of CPU. The number inside the arrow represents completion time. The total execution time in an iteration is determined by the thread with the longest execution time. In this example, partition P1 had the most data to be processed, and the total execution time is 16. The next figure shows a case that works stealing load balance scheme that traditional graph system used. At the time T1, CON0 completes the processing of P0 and can assist the CON1 to process the remaining data of P1. CON2 can also assist the CON1 when it completes its task at time T2. Finally, the total execution time is 7. Note that partition P1 is located in high latency NVM. This have suboptimal performance. So traditional work steering scheme can't handle the memory load imbalance. Our method is use data migration to deal with the memory load imbalance. We're migrating graph partition that has the maximum computing load from NVMe to DRAM at the beginning of the current iteration. As shown in the right figure, we first migrate graph partition P1 that has the maximum computing load from NVMe to DRAM. The following workload is similar to the work steering scheme. In this case, the total execution time can be reduced to 4.3, which is significantly improved than the work steering scheme. The second change is the data dependency among partitions, which will impact the effectiveness of data migration. To begin with, we first introduce the in-memory data structure of common graph systems, which include graph structure data, vertex value data, and vertex state data. Graph structure data includes the edge and vertex structure, which are usually stored in an edge array and a vertex array. Vertex value data store the value of vertices. Data current and data next arrays store the value data before and after the current iteration. Similar, current and next arrays store the state data before and after the current iteration. Here, we take literally an example. The figure is the execution flow of and memory access behavior of graph processing. We can see that the value array data next and the state array next are readily accessed and are located in different partitions. Interleaving access to different partitions were called data dependency. Thus, simply migrating a partition to DRAM cannot guarantee that all the dependent data of partition is also migrated to DRAM. We find that in graph processing, random access usually are dominant in the execution time. Inspired by this, we propose a dependency-aware graph partition strategy which coalesces the random access data required by a working thread in a single partition to mitigate data dependency. Based on these changes and motivations, we propose NVM graph, a scheme to deal with the load imbalance problems through data migration. Next, we are going to introduce our design of NVM graph. First, we show an overview of NVM graph, which mainly includes two modules, partitioning and graph processing. The partitioning module assigns the graph partition to different memories with mitigated data dependency, which enable and improve the efficiency of our subsequent data migration. The graph processing module performs the computation iteratively. At the end of each iteration of graph processing, we estimate the computing load of each partition, and only migrate data to DRAM where the benefit exceeds the cost based on lightweight performance model. NVM graph first tries to eliminate data dependency between different partitions, which coalesces the readily accessed data required by working thread in a single partition. The figure shows partitioning graph into two parts. NVM graph uses a vertex cut to evenly assign edge to partitions. Especially, NVM graph assign edge to a partition where their targeted vertices belong to, such as partition 1 has 6 outer edges, and their targeted vertices are in the set 3, 4, 5. Therefore, all randomly accessed data by a working thread can be in a single partition. Next, we introduce our Straggler-Aware memory load balance strategy. Previous data migration strategies use hardware or software assist method to monitor memory access, and then use history-based access information to guide data migration. These history-based methods are not suitable for graph processing because the predict hot data may become cold in the successive iterations. Thus, NM graph proposes algorithm-direct computing load analysis and performance model-direct data migration, which based on the logic of graph algorithms and their memory access behaviors. We'll introduce these two approaches in detail next. The algorithm-directed computing load analysis approach analyzes the computing load of each partition in the next iteration to find the straggling partition. Note that the computing load of graph processing is usually proportional to the number of active edges. Generally, vertices whose values are updated in the current iteration would become active in the next iteration, and the correlated edge of those active vertices would also become active edges. NM graph use a lightweight performance model to evaluate the benefits and the costs of data migration. The first equation is the benefit of data migration. The benefit stems from the reduction of total memory access latency when data is moved from NVMe to DRAM. The second equation is the cost of data migration, which consists of two parts. The first is the time spent in moving data from NVMe to DRAM. The second part is the time of evicting data from DRAM to NVMe and the increased memory access latency when the available DRAM is insufficient. Only when the migrate benefits outweigh the cost, NM graph migrates randomly accessed data blocks in the straggling partition from NVMe to DRAM across iterations. Note that we only migrate randomly accessed data, because that randomly accessed data in NVMe show higher latency and lower memory bandwidth than sequential access. And we only migrate data across iterations, since the data access frequency is not changed in a given iteration. Before going to the next section, we discuss the workload monitoring in NVMe graph. The right figure is a pseudocode of workload analysis. We can find that the entire workload monitoring requires accessing the state array, the vertex array, and the answer array. Monitoring workload in each iteration often leads to severe performance penalty. We design a periodical and threshold triggered workload monitoring mechanism to reduce the cost. First, we periodically conduct workload monitoring in a low interval rather than in each iteration. Thus can skip some unnecessary monitoring. Next, the workload monitoring is triggered when the variation of active vertices exceeds a given threshold. And the periodical monitoring may miss some iteration with significant workload variation. The threshold triggered workload monitoring is complementary to the periodical monitoring. Now we come to the evaluation part. We conduct experiments in a hybrid memory system using real NVMe devices, Intel Optane DCP-MM. The platform memory consists of 128 GB DRAM and 1 TB NVMe. We use 4 algorithms to evaluate the performance of NVMe graph on 3 datasets. The datasets are shown in the table below. The first First, we evaluate the performance of different graph processing framework in a hybrid memory system. All input graphs are partitioned into 4 partitions, with one in DRAM and others in NVMe. The baseline is the regular or hybrid memory system. From the figure, we can see that for algorithms such as BFS, SSP, CC, and PageRank Delta, NVMe graph achieve 90% to 40% performance improvement compared with the regular. This is because for this algorithm, the workload changes across iterations, and the NVMe graph can estimate the computing load of each partition and eliminate the straggler with the Straggler-Aware data migration strategy. Next, we evaluate the performance of graph algorithms using different data migration policies. The baseline is the regular without a data migration policy. Hunter-Weiser adopts a history-based data migration scheme which is not suitable for graph processing. Thus, regular with Hunter-Weiser causes 50% to 34% performance loss. OAM first employs an offline profiling tool, which analyzes all objects' memory access behaviors in different execution phases, and then places and migrates data online. Therefore, regular with OAM show roughly the optimal performance. An improvement of 24% to 44%. Our NVMe graph achieve performance close to that of OAM, no more than 6% performance loss. But we do not need an offline profiling. Finally, we summarize our work. First, we study the characteristics of NVMe and explore how hybrid memory affects the performance of graph processing. Second, we present a dependency-aware graph partitioning strategy to alleviate data dependency between different partitions. After that, we propose a Straggler-Aware data migration scheme to eliminate memory load imbalance among different partitions. I'd like to thank you for taking time out to listen to my presentation. Thank you.